We're now going to learn about the Fundamental Theorem of Calculus, Part 1. This theorem provides a formal statement of the inverse relationship between differentiation and integration. It's one of the most beautiful ideas in calculus and tells us how accumulation and rate of change are connected. Let's begin by looking at the accumulation function. G of x in our diagram represents the area under the curve y is equal to f of t, starting at a fixed point a, there's a, up to a variable point x, which is right here. G of x is the definite integral from a to x of f of t dt, and it's also called the area so far function. It tells you how much total area, distance, volume, or any other quantity has accumulated up to that point. Now that we understand that g of x is the accumulated area, the next question that we need to answer is how fast is this accumulated area g of x increasing as x increases? As x increases by a small amount, the accumulated area is also increasing by a small amount, and this amount is shown here in pink. This new area is equal to f of x times dx. That's just the height times the width. To find how fast this accumulated area g of x is increasing as x increases, we need to look at the rate of change of the area g of x. That rate of change is equal to the derivative of g of x, and it's equal to the new area divided by dx. Up above, we saw that the new area was f of x times dx. We now divide that by dx, and we get that it's equal to f evaluated at x. So the rate of change of the area g of x is just f of x. The accumulation function g of x is an antiderivative of f of x because its rate of change equals f of x. The Fundamental Theorem of Calculus, Part 1, formalizes this connection between accumulation and rate of change, and it shows us how derivatives and integrals are related. Let's now see what this theorem tells us. The Fundamental Theorem of Calculus, Part 1, tells us if f is continuous on the closed interval from a to b, then the function g is defined as g of x is the integral from a to x of f of t dt, where x ranges between a and b. G of x is continuous on the closed interval from a to b, just like f was, and it is differentiable on the open interval from a to b, and the most important part is that the derivative of g of x is equal to f of x. I've summarized this down here in our blue box. If g of x is the definite integral from a to x of f of t dt, then g prime of x is just f of x. Let me say this a little bit more simply. The derivative of a definite integral with respect to its upper limit, which in this case is x, equals the value of the integrand, that's f of t, evaluated at that upper limit, which is x. We're now going to learn all about the Fundamental Theorem of Calculus, Part 2. The Fundamental Theorem of Calculus, Part 2 provides a direct method for evaluating a definite integral using antiderivatives. This is going to be a lot easier than having to use Riemann sums. Let me just remind you what the Fundamental Theorem of Calculus, Part 1 tells us. It tells us that if we have a function g of x, which is the definite integral from a to x of f of t dt, then dg dx, or g prime of x, that's just the derivative of g, is equal to f of x, which is the integrand evaluated at the upper limit of integration. Since g prime of x is equal to f of x, we can say that g of x is an antiderivative of f of x. To get to the Fundamental Theorem of Calculus Part 2, we have to complicate this a little bit, and we're going to let a function capital F of x be any antiderivative of little f of x. And what we're going to do is we're going to compare this to g of x. Since any two antiderivatives differ by a constant c, we can say that capital F of x minus g of x is equal to a constant c. We can then rearrange terms and say that capital F of x is g of x plus c. I'm going to put a red check here because we're going to come back to this a couple of times. What we're going to do now is we're going to see how we can use the expression that I marked with a red check and the definition of g of x in the green box above, right here, to find a formula for the definite integral of f of t from x is a to x is b. So our goal is to find a formula for our definite integral, and that way we won't have to keep using Riemann sums. How we're going to do this is we're first going to let x be equal to a. This gives us that capital F of a is equal to g of a plus c. We're just substituting in that x is equal to a. This function here comes from our green box up above, and that's what g of x is equal to. Now we're going to let x be equal to a, and notice that a is now in our upper limit, and we're integrating from a to a, so that integral is equal to 0. And we can say that f of a is equal to c. Let's put that in our pocket for a minute, and we're going to come back to it. Now what we're going to do is we are going to let x be equal to b. So let's come up here to the right, and we let x be equal to b, and we get capital F of b is g of b plus c. Now, we know what c is, and we can substitute in that c is capital F of a. Now what we're going to do is look at this formula for our integral, and we're going to let x be equal to b. And that gives us that g of b is the integral from a to b of f of t dt. Hang with me, we are almost done. What we're going to do is we're going to take this expression and put it up into that equation. This gives us capital F of b is the integral from a to b of f of t dt plus capital F of a. Now all we have to do is just switch around terms. We'll pull the capital F of a to the left, switch the sides, and we end up with the integral from a to b of f of t dt is equal to capital F of b minus capital F of a. And that's exactly what the Fundamental Theorem of Calculus Part 2 is. The Fundamental Theorem of Calculus Part 2 tells us that if f is continuous on the closed interval from a to b, that's super important. The theorem does not apply if f isn't continuous on that interval. Then the integral from a to b of f of t dt is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. In other words, it's a function such that the derivative of capital F is equal to little f. I'm going to now say this in a way that makes it easier when you go to use this theorem. Our theorem tells us that the definite integral of a function equals the antiderivative of that function evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And that's all there is to it.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.